You can use the same idea back.
All right, hello everybody, welcome back. Let me share my screen. Okay, so today we are going to continue on our lecture on finding similar items. And I think we will have time to talk about our recommendation systems. We were somewhere here. Let me just briefly recap on the whiteboard. All right. So still remember what we have been working on this week? This large matrix, we want to be able to compare documents, but we have lots of dimensions, column 0 to column 10, median, -1. And we do have a way to help us do this. We say, hey, let's create min hash signatures. So you have D0 to D1 median -1, and your columns becomes signatures. much smaller. And we also talk about one of the application for this work is each D is a document. And we can create shingles to represent a document. So essentially your D0 would be shingles, right? So it could be shingle 1, shingle 2, and so on. And this is a set. So to represent a set in a matrix like this 10 millions minus 1, this is all possible shingles, right? And in the matrix, if your D0 contains that shingle, you will have 1. If you don't, you have a 0. So that's it. And to compare two rows, to figure out their similarity, because these are two sets, so we are using our Jacquard similarity. Great. Now, once we have this, we have much smaller dimension here based on our min hash functions. But still, we have lots of documents that we want to compare. So the number of document pairs that we have to compare will be C1 million choose 2, similar to 1 million squared divided by 2. And this is not good, right? So we want to be able to have some sampling strategy to see what are the documents here we really want to compare if we want to find a similar document for D0. Okay, so how do we do that? We say we want to do similarity. Sorry, we say we want to just generate samples. So here comes the LSH. Okay, so this might be a little bit confusing, so just bear with me. If you have any questions, just ask. D0 to D1 million minus 1 again, and you have signatures from S0 to S1000 minus 1. So we are saying that instead of comparing these two directly, we want to take some samples from D0 and let's say D1. And if the samples tell us these two documents are highly likely to be similar, we want to compare them. So how do we do that? We can start by splitting your signatures into multiple bands. I know this is different from the slides because your slides is a transpose matrix, but I think this way you understand how it will work. So in this case, let's say we have, now you have 100 signature, and let's say we have 4 bands. How many signatures do you have in a band? Anybody? 100 signature, your band equal to 4. So great, your R will equal to 25, right? That's 25 times 4 equal to 100. And each band here is your sample. So when we look at samples, that means we are looking at this 2 document. We say, hey, do you have the same value? Okay. If you don't, let's move on to the next sample. Do you have the same value? If you don't, let's move on to the next one. If you don't, we still need to compare the last sample. And if every sample tells us they are not similar, we say this could not be similar. We don't want to compare them. So that's the basic idea. But it sounds really dumb, right? Because if you want to compare every band, which means you still have to compare every signature, how would this help us to save time? So in practice, if you read your textbook, each of the sample is hashed. So it's got hashed into, let me see, how do I draw this? Each sample is hashed, is the input of a hash function, they should be using the same hash function because they are the same band. They go into this hash function, and the hash function will give you some numbers. Okay, so the first one is the D0, the second one D0, this band. And we do the same hash, D1. Okay, and this will give you a number. So the number could be 25. I'm making this up. So 25 and 25. This means what? Well, this means they are identical. This is the same as this because the hash function gives you the same value. This also tells you what? This tells you your hash table does not have collisions. If you think about our bucket example, this hash function gives you enough number of buckets. When you have a unique key, you will have a unique value, okay? And in this case, this end is a key, and this is your value. Are we good so far? Yes? And to think about this, it's really easy to find this hash function. When you use Python, there are libraries that you can do this because all these bands are just strings. And we say you are equal to 25. So the band here would be a string of 25 components. First component, and this is the 24 component. So, right? So you're taking a string, you hash it into one number, and these are pre-calculated. So when you have a document, you pre-calculate all the string values. Now you don't have the band anymore, you just have values. This is 25, this is 25. And when you hash this yellow part, it might be a 4, this might be a 3, 2, 2, and 1, and 4. If you just look at here, I made up these numbers, but what does this tell you then? If you're using all the same hash function, let's just call this hash function h. I couldn't decide which one I want to use. Let's call this hash function x. Okay, assuming we use the same hash function for every band. What do all this number tell you about the bands? Anybody? Well, first one we know is these two bands. They will have exactly the same strings, right? What about this? What does 4 and 3 tell you? So 4 means when we take this, use the hash function, it hash into a place with a value equal to 4, right? When we take this, the hash function will give you somewhere here and give you a value of 3. So we know these two, the yellow blocks are not the same. How about 2, 2? We know they are the same. 1, 4, we know they are not the same, right? And also, because we know these are the same hash function, we know this block would have the same value as this block, but it doesn't really matter to us because they are at different location. So for this case, half of the blocks are identical. So we say, all right, these two might be similar. We want to compare them, right? Because more than one block is similar. So think about this. This is a sampling-based approach, which means you are always going to have false positives and false negatives. What is a false positive in this example? If we want to find similar documents to D1, and we are using this LSH to identify candidates that could be similar to D0, what would be your false positives? Anybody?
You're falsely categorizing two documents to be similar when in fact they're not.
Great. So that means we say they are candidate, but they are not similar. How about false negatives?
They are not candidates, but they are truly similar.
Great, not candidate, but they are similar. So this gives you some, well, if you look at this description, this means what? This means we have to define something called similar, right? We have to define what we mean by similar, or you don't have any ground truth to be able to generate false positives and false negatives. So that means LSH is pretty cool. You, based on your application, you say, hey, my definition of similar is 80% Jakarta similarity. So if you look at the sentences here, again, false positives means your LSH identify them as candidate. But this true pairs, this one pair are actually has less than 80% similarity, right? And if you look at your false negative, this is LSH says they cannot be a candidate pair, but the similarity is larger than 80%. So what does this tell you then? This tells you that your false positives and false negative rate depends on how you define your similarity and what else, and depends on what? What in LSH would affect how you decide a candidate? Well, your hash doesn't really affect it, right? It's the goal for, the only criteria for the hash is if you're the same input, you will have the same output. That's it. What else will decide, what else has an impact on which pair would be a candidate? Sample, great. So block size. So when we talk about sample, we talk about block size, right? So how many bands do you have and how many signatures in a band? So that means to look at your false positive and false negative rate, now we collect three things: similarity, so application, and your B and your R. So what would be the problem of false positives? Why are they bad? In this case, what do we want to do? So let's start from here. Your goal is to take D0, you find all the similar documents, right? And you say my similarity definition is somewhere here, 80%. I want to find all the document that has 80% similarity to me, but I don't want to compare everyone. So I use this LSH. What would high false positive rate affect my approach or result? Think about this process. You take D0, you compare all these hash values with everybody else's hash values, right? And then you find candidates. Let's say this one, D1 is a candidate, this one is a candidate, this one is a candidate, this one is a candidate. what if you have false positives? Well, let's say this one is false positives. This one is false positive. Can you remove them? Well, assuming your LSH is working very well, that means you are going to have many candidates or a small set of candidates. Small set, right? Your goal is to remove as many documents as possible if you don't want to compare them. So if you have false positives, now you have a small set of candidates, you can actually just compare D0 to every candidate. And can you remove false positives? Right, so someone has the correct answer. This means you can remove false positives by verifying this, right? Exactly like what we did in the sampling approach. But the downside is you just more computational time, right? If your false positive rate is high, you're wasting time comparing them. How about false negatives? Would you be able to recover them? Well, again, like sampling, you cannot really recover your false negatives because you do not know whether or not this one is true positive or this one is true positive unless you compare them. Okay, so are we good? I think this gives you the full picture of LSH and all the shingles and min hash. But most importantly, now we are here, we need to, let's go back to the slides. The question becomes, since we know both, we know that to control your false positive and false negative rate, you need to look at your applications similarity threshold. You need to look at your B and you need to look at your R, right? So we want to know how this 3 would affect your false positive and false negative rate. And that's today's topic. So if we look at this, okay, so there's a question, what was the first one? You mean the first one that affect your false positives and false negatives? The first one is your application defined similarity, because our goal is to find similar documents, right? Similarity in Jakar distance. So it can be 80%. I will show you guys this, but let's look at the slides first. Okay, so still remember this. This is super easy to calculate, but let's do it very quickly. Say we want to compute the probability that two signatures agree on all rows in at least one band, right? This means they are candidate pairs. To be able to do that, we want to compute this complement probability first. Then we will have the real probability that we want to calculate. So how do we do this? We look at the complement probability. We look at the probability that they disagree in at least one row in a band. Okay, so this is for one band. And because we have B band, so this complementary probability becomes Q to the power of B. The probability of rows in a band agree is S to the power of R. And I think you guys all know this because for one row, one signature to agree between two documents, the probability is S, which is the Jakar similarity between these two documents. And because you have R rows in the band, so it's S to the power of R. So Q will be 1 minus S to the power of R, and then you have your P. Okay, so this is very easy, but this is very, very important. When we look at this function, this tells you the probability of becoming two pairs, the probability of two documents become a candidate pair. And this probability is based on Jacquard similarity, R and B. So if we plot it on a chart, it looks like this. So I think we were here last time. And this chart is not particularly easy to understand. So bear with me here. Here's your Jacquard similarity. Here is the probability of becoming a candidate. So you have a function here. You have your P, which is this. You have your S, which is your x-axis. Then you can plot this line, right? Given that you have B and you have R. So why is this line important? If we just look at any location, for example, we say we have a document pair. They are 80% similar in Jacquard similarity. Okay, and 80% similar, it will give you a probability of them becoming a candidate pair. So this could be 97%, which is pretty high. Only 3% of them will not be a candidate. Are we good so far? Anybody has questions? This is based on one row. No, this is based on, this is the entire document. So Jacquard similarity between documents, D1 and D2. The note to the right. Oh, no, this is talking about the straight line here. Let's ignore this straight line. Let's look at this curve first. The curve is this function, B equal to 20, R equal to 5. Okay, so two documents, 80% similarity, 97% of chances to become a candidate. So think about this. If in your document archive that you have a huge archive, right? And in that archive, you want to find all document pairs that have 80% or more Jacquard similarity. And based on your some prior knowledge, let's say you can assume that you have 100 documents, that 100 document pairs that will have exactly 80% Jacquard similarity. Okay, and this tells you, based on this chart, how many of these 100 pairs will become a candidate. Anybody? 97, great, because here you have a 97, right? So that means this line tells you your true positives, right? This is 97. 97 of them becomes your candidate. And what is here? This part. This is how many? 3. This 3 becomes your false negatives, right? And they are false negatives because you want them to be similar, because I said I want my similarity threshold is 80%. I want everything that's equal, every pair that have equal or more than 80% of Jacquard similarity to be candidates. But you still have 3 here. So this becomes your false negatives. So you can see that this slide looks very interesting, because if you start to look at these different locations, this is say 70%. This means many pairs. Let's say you have another 100 pairs here in your archive that are at 70% Jacquard similarity. And let's say this number is 95%. Okay. So what's the length of this line? Yeah, I will tell you. I'll tell you with this example. So the question is why Fn's not Fp's. I'll tell you with this example. So bear with me here. 70%, my similarity threshold is 80%. Smaller than 80%, I don't care. I only want to have larger than 80%. Okay. So let's say in my archive, I have 100 documents. They are 70% similar. They have 70% Jakarta similarity. So what is the length of this line at 70%? 95. This means out of these 100 pairs, how many of them will become candidates? Anybody? "95 of them will become candidates. But do I want them? Do I want them to become candidates? No, right? Because my threshold is 80%. They are smaller, their similarity is 70% already. It's smaller than 80, so I don't really want this. So these are your false what? Positives or false negatives? False positives, right? So your false positive is here. If you understand this, we are going to look at an example that will help you to better understand this. But just given this, what we want to do is we want to be able to spot false positives and negatives on the chart, and we want to understand how the curve would be able to change its shape based on this R and B changes, and how to determine good similarity threshold. Sometimes it depends on your application, but let's start here. So if B equal to 20, R equal to 5, let's say your S equal to 0.8. Remember that P equal to 1 minus S power of R, the power of B. Okay, so based on this, you can calculate all these interesting scores and you can create a table like this. So this tells you that for two documents with 80% Jakarta similarity here, there are 33% chances in agree in all 5 rows, which is here. And 1 in 3,000 pairs will not become a pet candidate, right? So that's why you have a really high probability to become a candidate. So based on this, we also know this false positive, false negatives, and true positives. False positives, I think we covered this a long time ago, but precision and recall are commonly used for information retrieval. So precision tells you that this is the true positives you identified based on everything you identified, including the true positives and the false positives. Recall tells you, this is the true positives you have, and this is all the true cases in your ground truth data set, right? This is the true cases you identified. These are the true cases that you did not identify. So if you're not familiar with these two terms, well, let's look at this. When your false positives here goes down, will your precision go up or down? This one goes down, your precision will go up, right? It does not affect your recall. For your false negatives, when it goes down, this one, the recall goes up, but does not really affect your precision. So why do we care about these values? Why? Well, because there's no perfect machine learning algorithm or data mining algorithm. You always have some errors, right? When you have error, you want to be able to, so let's just make this, wait. Okay, our assumption is you are always going to have errors. Errors exist. Assumption 1. Assumption 2, you can always tune your algorithm to First, maybe you can make the errors smaller, or you can have types of, I'm not very good at writing with my mouse, but bear with me. Types of errors can be tuned. So for example, let's think about your COVID test. When we perform a COVID test, what is true positive? You predicted COVID positive and get infected. Okay, good. And you're infected. What is a true negative? You predicted not COVID and not infected. What is false negative? False negatives is you predict false, but it's actually infected. And false positives, sorry, it should be false positives. False positive is you say it's, the test says it's predicted true, you're infected, but you're actually not infected. Okay, so you can have 4 cases. But let's assume in your COVID test, you are measuring something in your blood, okay? And you have a threshold. You say, based on this threshold, I can adjust this threshold to have different error rate. By adjusting the threshold, I can have higher false negatives because now I predict many things that are not infected, but they're actually infected. Or I can adjust my threshold to the other direction. This way I predict many positives, but in fact, many of them are not affected. So what do you want to do if you're administrating this test? Do you want to have more false negatives or more false positives? Remember, our assumption is there's always errors, so you cannot ignore them, right? So what do you want to do? How do you want to change your threshold? Do you want to have higher Fn and lower Fp, or lower Fn and higher Fp? It's usually like this. All right, so people are saying we want to have more false positives and lower false negatives, right? Because in this case, especially in the medical domain, you want to be able to eliminate false negatives by increasing your false positives. Because if you have false positives, you can still have, like what we did, where you can have second steps to verify it, or you can just have some precaution to make sure that they are not really negatives. But if you have lots of false negatives, you cannot really remove them. And this is also true for many of this automatic X-ray image processing machine. So many people are using computer vision to help identify possible lung cancer patient, for example. And you want to have very high false positive rate so that you can have low false negatives. You don't want, if something looks strange, you want to alert the doctor to manually look at it, right? So that means your false positive will be high, but your false negative rate will be low. All right, so this is just something to keep in mind, that for all the algorithms that we cover in this class, almost every algorithm, you will be able to tune your algorithm to have either high precision, low recall, or low precision and high recall. Okay, so we talk about false positives and false negatives, but in our example, false positives are the candidate pairs that they are not similar, the documents that they are not similar, but they are some of their samples got hashed into the same buckets, so they are candidate pairs. False negatives are the document pairs that are similar but not hashed into the same buckets. Some of their samples, well, all of their samples are not hashed into the same buckets, so they are not candidate pairs. If we look at this chart again, we know that below the line is the predicted positives, right? Remember our example, 80%. And I say this is 97% here. And I tell you there are 100 document pairs at 80%. And you told me that there will be 97 of them become candidates, right? So these are below the curves are predicted positives. Above the curves are predicted negatives. So if we add this S line, this is our threshold. This is our application defined, manually defined threshold. We say we only care about Jakarta similarity larger than 8, in this case, 50%. If it's lower than 50%, we don't want to compare them. So this means everything to the right of this line are actual positives, right? Because everything to the right of this line has larger than 0.5 Jakarta similarity, right? Remember your x-axis is the Jakarta similarity between documents. Everything to the left is the actual negatives because we don't care about them. If you put these two together, area below the curve, predicted positive, above the curve, predicted negatives. Area to the right of the line are the actual positives, to the left of the line are actual negatives. Then where are your false positives and false negatives? Well, here, right? To the right means you are positive, but you were not selected as a candidate. So you are false negatives. To your left, these are because you are below the line, so you are identified as positives, right? Means you are candidates, but since you are to the left of our threshold, we don't care about you, so you are false positives. So which is pretty cool. By looking at this line and your threshold, you will be able to spot the sizes of your false positives and your false negatives. Ideally, we want something like this, right? No false positives and no false negatives. If you can identify the similarity threshold based on your application, we just do this. Everything below this similarity threshold has 0% to become a chance to become a candidate. Everything above this threshold has 100% chance to become a candidate. Right. However, that's not possible. If two sets are identical, two documents are identical, they will have the same signature. So no matter how many buckets you have, what's your BNR, they will for sure to be hashed into the same buckets, so there's no error. But many cases, we are not just care about identical documents, we want to be able to find similar documents, right? And we define similarity, say 80%. So when we have 80% similarity, when we care about not just identical documents, all these similar documents are still possible to hashed into different buckets because the way we split the signatures into bits, and this can become your false negatives. Also, these similar signatures may happen to agree in some band, even one band, they will end up in the same buckets, and this becomes false positives. So let's look at some example for false negatives. Let's say your similarity threshold is 0.8, 80%. If your Jakarta similarity is larger than this, they are similar, we want to find them. And say your B is 20, R is 5, Jakarta similarity equal to this for these two documents. So they are similar. So what is the probability that your two documents are not identified as a candidate pair, which means they are false negatives? The probability of them identified as a candidate pair in a single band is this, right? R is 5, and the Jaccard similarity between two documents is 0.8, so it's 0.328. The probability of them are not candidate pairs in any band is a very small value, because not only you have to consider one band, you have to consider all the bands, right? Remember our probability function, this function. So 0.35% of the chances that these two sets with similarity 0.8 are false negatives, which is pretty good. So it's very, very small chance. When we look at false positives, let's say, again, your similarity threshold is 80%, the same B and R, and you have two documents, their Jaccard similarity is 0.3. We do not want them to be a candidate, right? So what's the probability of them becoming a candidate in a false positive? If we look at one band, it's 0.3 to the power of 5. That's a very small number. But you do have multiple bands, so it becomes a larger number, 0.04. So 4.7% of the chances that the two sets will, with similarity of 0.3, 30%, will end up in the same buckets and become your false positives. If you look at the chart, it's here. This is the 0.047 here. This number is here. And remember, this is 0.3, right? This is how we calculate it. And this is your 0.0035. That's this tiny places here. And if we just list all the probability based on the similarity value, this is your table, and this table represents this blue line. So pretty cool, right? You can start to see that when you have very small similarity, you have very small chances to become a candidate pair. When you start to have larger similarity, you have larger chances. So the difference between PCY and LSH is your PCY, because they all use buckets. In PCY, there's no false negative. If an item pair is not in a frequent bucket, we know it's not frequent. You can have false positives, but your last pass, your second pass, will rule them out, right? Because you're going to count them again. LSH, you can have both false positives and false negatives, but you can also eliminate false positives by compare the original string, or sorry, original documents or the signature. We are going to talk about that later today. All right, so then next we are going to look at how we how the curve will change its shape if we varies R and B. But let's take a break for 10 minutes and come back at 7. If we have any questions, feel free to post them in the chat. I will answer them when I come back. Hello, I'm back. Let's continue. Okay, so how does the curve will change the shape? When we do have R equal to B equal to 1, this is highly unlikely because this means you only have one signature, right? The probability of becoming a candidate would be what? S, right? R equal to 1, B equal to 1, and cancel it out. P equal to S, and this is min hash. The probability of becoming a candidate is your signature, which is your Jakarta similarity. So if we look at the chart, your probability of becoming a candidate becomes this. Similarity and the probability are the same. However, we say this is not going to work because we always have more than one signature. So what would be a real scenario? So from here, let's look at if you have R equal to 5, B equal to 1, the probability of becoming a candidate, we already know how to calculate this. We know how to generate this table. And R equal to 5, B equal to 1. Okay, B equal to 1, so no B. Cancel it out. P equal to S to the power of R. What does it mean then? Well, this means if your S is small, like here, the probability of becoming a candidate will be even smaller. If your S is large, it will be smaller, but it's not significantly smaller. Okay, so if you look at this table, you know that P is much smaller than S, needs very high similarity, needs very high S to become a candidate. So for example, even if you have 0.9, you still only have 60% chances to become a candidate. So this means we can reduce false positives, right? R, high number of R will help you reduce false positives. If we look at this R equal to 5, B equal to 1 again, P is much smaller than S, especially true on small s values like here, because P is now 5 orders of magnitude of smaller than S, and that's 5 orders is here. So your R number, larger R, makes dissimilar pairs even more dissimilar in terms of P. So this is talking about P. This is talking about S. If we look at the chart, this is R equal to 1, B equal to 1, just as a reference. When you have a larger R, it pushes the curve to this side, right? So everything here has very small probability. Not until you get to somewhere here, you start to have larger probability of becoming a candidate. But just an important note here is that we know these two lines are not comparable because R equal to 5, B equal to 1 means you have how many signatures? 5. And this line means you have how many signatures? 1. Okay, so it's not really comparable because we're talking about different signature sizes. However, you can see that if you have larger R, you can push the curve to the right. If you keep increasing the R, you push it even more to the right. That means the probability of becoming candidate is always very, very small until here, right? So summary, if you fix your B and you increase your R, you can reduce false positives, increase false negatives, okay? Because it's really difficult to become a candidate. So let's look at if you fix R and varies B, what would happen? Probability of becoming a candidate, our old friend, B increases the probability of similar pairs placed in the same bucket, and it will reduce false negatives. Okay, so if you have a larger B, this will be a larger value, and the probability of becoming a candidate will be what? Oh, sorry. If you increase B, this will be a smaller value because this 1 minus S is always smaller than 1. If we look at the chart, it looks like this. This again is your R equal to 1, B equal to 1. If you start to increase B, you can see the line got pushed to this direction. If you look at here, when you have similarity equal to 0.1, you have 40% of the chance to become a candidate, right? 0.1. If you have 0.9, you have really high chance to become a candidate, always almost 100%. So everything is above the straight line, and especially towards here. If we further increase your B, it's even moved toward the top left corner, and if you have a Jaccard similarity larger or equal to 0.6, now you're guaranteed to become a candidate. Okay. So if you look at here, S is always smaller than 1. 1 minus S is always smaller than 1. So if it's a smaller than 1 value, if this one increases, it will only decrease this value, right? So if you decrease it a lot, your P will be very similar to 1 because this whole thing becomes a very small number. So in summary, if you increase your B, it will help you to reduce false negatives and increase false positives, right? Because high probability to become a candidate, so this is reduced. However, some of them we don't care, so you are going to increase your false positives. So let's now look at both B and R larger than 1. So this is your normal case. You have an N number of signatures that you can play with, and you want to decide on the R and B. And R times B is always equal to your N. So in this case, if you have R equal to 5, B equal to 20, these similar pairs becomes even more dissimilar. Okay. Right? So 0.2 will have very low chance to become a candidate. And we know this is largely due to R, right? R push it to the right. Similar pairs becomes even more similar. So 0.7, you already have 0.975 chances to become a candidate. So similar pairs. We know this is largely due to B because you push the curve to the left. So if we put them together, this is your curve. Remember, if you only have B, it looks like this. If you only have R, it looks like this. If you have both B and R, it looks like this. Right? So if we look at the decomposition of the graph, R pushes the graph to here. B pushes the graph to here. Increase B will push the graph even further here. Increase R, push the graph even further here. An important note again, these are not comparable because they are having different N. All right, so the number of signature here is 100, number of signature here is 200, number of signature here is 300. But this is only for you to see that if you fix one number and change the other number, what would happen. So how do we really determine the similarity threshold? Or even better, how do we even determine the B and R when we have a fixed N? So you can manually set it. This is the most common way to do it because your application usually have the threshold you want to do. And then based on this threshold, you can set your B and R. So let's say this is the threshold that defines how similar two documents have to be. in order for them to be regarded as the desired similar pair, right? So this is very much application defined. You can also set it equal to p equal to 0.5 if you already have a preset b and r. Okay, so important here, you set it into p equal to 0.5 when you have b and r already set. This means the curve rise halfway. This is called the predicted threshold, and I will explain this on the next slide. So if you look at the chart here, based on this p function, if you already have r, you already have b, you have a curve, right? When you have a curve, let's say b equal to 20, r equal to 5, you have a curve, and you know the predicted threshold, 0.5. When you have 0.5, based on this line, this probability line, you know that your Jaccard similarity is 0.51. So what does it mean then? This means if your application cares about 0.5, anything above 0.51, this is probably your best curve. Why is that? If you look at this, 0.5 is somewhere here, right? Probability 0.5. Now you have 0.47, so somewhere here. Everything below here would have a low probability to become a candidate. Everything above it will have a high probability to become a candidate. Okay, that's why the predicted threshold is usually important. So, but if you don't have this, if you don't have B, you don't have R, you only have N, this is the most common case. You only have N, you want to decide B and R, okay? So how do you do that? Well, you first find your threshold here. Let's say 0.8. Your application tells you that everything above 0.8 is important. Then you construct this line so that this halfway point of 0.5% probability will be here. So your line will look like something like this. And you can figure out what would be the good B and R that will have a predicted probability like this with your threshold here. And what does this mean? This means everything below here would similar to this, would have a low probability to become a candidate. Everything here was similar to this that will have high probability of becoming a candidate. So you can adjust this B and R to achieve your goal. And if your N, the length of your signature is 100, R could be 5, B equal to 20, or different values. Only thing that you have to follow is your N is always 100. So if you look at all these three charts, you can see they would change shape, change locations on the chart, and you can look at the predicted threshold, right? So if your application has, maybe this is 0.9 Jaccard similarity, then you want to use this setting, R equal to 20, B equal to 5. If your application says, I only care about what, this 0.75 maybe, then you can use R equal to 10, B equal to 20. If your application says R equal to, if your application says 0.5 is what I want, then you use this line, R equal to 5, B equal to 20. It doesn't have to be exact because the midpoint tells you the probability of becoming a candidate would be low here, right? And would be high here. So typically for the predicted ones, if you have larger R, you have larger threshold because larger R value will push the curve to this direction, right? Then your midpoint will somewhere here, give you a threshold here. If you have larger B, you have larger threshold. So your application defined similarity will be 10 to on this side of the chart. So increase the predicted threshold will be able to reduce false positives, less checking time later, because if you want to reduce false positives, if you want to verify them, you have to compare every predicted positive that include false positives. Decrease the predicted threshold will reduce false negatives, but longer checking later, okay? So how do we do all this? So these are all R and B. How do you set them and what do they mean about, in terms of your false positive and false negative rate? But in general, I think we did this on the whiteboard. I just want to say this again. If you want to find similar documents, you have a large set of documents. You construct your K shingle, right? You pick a nice K. For emails, you can pick 5. Then you turn them into integers. That means each shingle, you have an integer to represent it as the ID. Then you can build your min hash signature of length n. You can pick your n. So remember we talked about this 5 shingle. You have 14 million, some large number of shingle sets. And you pick an n, could be like 2000. You choose the B and R based on your signature length, and you adjust your threshold based on your application defined similarity, okay? And here's your guidelines. Then you can start to construct candidate pairs, look at the signatures of the candidates, and may check the documents if their signatures are similar. This means when after you generate the candidate, you can really take the either min hash signatures of the documents or the original K shingles, depends on how much computational power you have, and really verify if they are similar. So one thing that's not listed here is how we generate candidate pairs, right? But I think I showed you that on the whiteboard. For each band, you use a hash function to return a value so that you only compare the hashed value. You don't compare the candidate bands. Some example here. So let's say you have 1, 2, 3, 4 documents, and you have band 1. This is only one band. And document 1 has 1360. Document 2 has 2310. 3 has this and this, right? You can imagine that you have more columns here because this is only band 1. If you have this in your database, you'll be able to write a query like this. This is saying that let's select the documents from all my documents where the band 1 min hash algorithm 1, first signature equal to 1, second equal to 3, third equal to 6, and 0, right? This is finding all the documents that have exactly the same values in band 1. Or band 2 are the same because we are looking at this document 1. So all these numbers are not listed because they are here. Or band 3, band 4, and band 5, right? If note that you have OR here. As if one band return true, that means one band pairs is identical, then you want to compare them. But one thing you can look at here to look at their code to understand the algorithm. But one thing that's really interesting here, and even the webpage didn't mention, is if you are doing this, you are relying on your databases to do the comparison really quickly, right? But actually for each pair, you still have to compare every signature in the worst case, right? Because it's OR. So locality sensitive hashing tells you that without comparing this, you just take this 1360, you hash it, then you have a number X. You just compare all the hash values without compare individual numbers, then you're good. All right, that's everything I want to say about LSH. Any questions before we move on to your recommendation systems? Awesome, no questions. So for your assignment 3, assuming you are still working on assignment 2, but your TA is going to release your assignment 3 any days now. The first part of your assignment 3 is to use this min hash and locality sensitive hashing to compare business reviews. I think it's to compare business based on their reviews. Then you can use the result to build a recommendation system. That will be the second part of the assignment 3. Or you can use the methods that we're going to cover today. I think it would be the method that we're going to cover today to build a recommendation system. But eventually in your final project, you are going to enhance your assignment 3, and you are going to compete with other students and your TA for building a very accurate recommendation system. Okay, so second part of today's lecture, we are going to talk about recommendation systems. And I think we are going to be on the topic of recommendation systems for a while. It's a very interesting and practical topic. We are going to cover 3 types of recommendation systems, but mainly the second type. Additional readings. You have to read this because the content might be used in your quizzes or in your exam. So take a look at the Wikipedia definition. It's pretty comprehensive. Look at the motivation, why we are building a recommendation system, and look at recommendation system paper and a survey. Okay, so lots of readings, but these are fun readings. So what would be an example of a recommendation system? You have customer X comes in. This customer X buys Metallica CD and also buys Megadeth CD. Your customer Y comes in and does some search on Metallica. What would you do? Oh, sorry. Yeah, let me upload the slides first. Thank you. Okay, so you should be able to see the slides on Piazza. Okay, customer Y comes in, customer search for Metallica, and you will be able to say, hey, would you be interested in Megadeth based on the data collected about customer X? Right, so this is one type of a recommendation system. But what information have we used here? Does this strategy care about the content? Do we have to know what exactly is Metallica, what exactly is Megadeth? Not really, right? We only know that someone purchased them together, so they could be similar. This is very similar to all this data-driven method people are talking about today. You don't really need to understand the content. You can base on large data sets to figure out this similarity and make the recommendation. It's also very similar to what we have been doing for the mining frequent item set or similar items, right? If 2 items appear together many, many times, we'll be able to make the recommendation. So in general, a recommendation system, you have a customer, you have a set of items that you want to recommend. This could be your products, or it could be websites, news items, blogs, documents, and all that. First rule is we want to be able to make everything available. So everything here available to the user. And since you have a lot of things now, what your real task is to help them find new content, right? They might not know they like it unless you tell them. So how do we do this? Your customer search for something, we make some recommendation, and some examples would be Amazon, Netflix, movie lenses, music, YouTube, Google News, Xbox Live, and all that. People have been criticizing this type of all these recommendation systems. Say it always recommend you stuff that you would be comfortable with, right? It will never recommend things that outside your comfort zone. And we're going to look at some of the algorithms to see if you would be able to build a recommendation system that might be able to overcome all these difficulties. Well, especially like during election time, or when the society have a really important issues, you can start to see many times Facebook or other content recommendation system will recommend something that within your comfort zone. So you will never be able to hear the voice from other people or the people that are different from you. And that's recommendation system that I can only say they do a pretty good job on looking for the things that you like. So types of recommendations, 3 types. We have editorial recommendations, hand curated. These are the list of favorite, list of essential items. These are really hot keywords. If you search them online, you will see many websites just dedicated to do this, right? So things like top 10 email apps for Mac users in 2020. This is usually somebody pick them, editorial and handcraft. Or a simple aggregate, top 10 most popular recent uploads. So you can see this very often in all these app stores. Or you have the last one, tailored to individual users based on your previous interest, and will be able to generate this too. And this is very common for the Amazon, Netflix, the online platforms when they have large consumer base and large product base, and they know a lot of things about you. Formal model about a recommendation system. Say we have X, this is a set of customers. S is a set of items. Users have preferences for certain items. This means you already have some information about your users. We want to be able to extract preferences from your data, and we call this a utility function, which is X by S, and the value would be R. This is a matrix. And R is a set of ratings, and this R is a totally ordered set, like 1, 2, 3, 4, 5, or numbers in a range of 0, 1. Okay. Let's look at the utility matrix example. You have people, you have movies. For each user item pair, Alice and Avatar, you have 1. So this could be a rating, right? Alice has rated Avatar for 1. But this also can be a purchasing history table, right? You have 1 means you have purchased it. If you have 0 means you have not purchased it. And the matrix is typically very sparse because most of the entries are unknown. So why? Well, because typically you are going to have many of the items, and you have many users, and most users do not rate most items. Well, you can ask yourself, when was the last time you rate an app in the App Store, right? It will keep bugging you, ask you to rate it, but you probably always click on no. So the goal for a recommendation system is to predict the blanks in the utility matrix. It will be able to tell us if Alice would like pirates, would David like Avatar, but the goal, again, is not to predict every blank entry. We only want to discover some entries in each row that are likely to be high. Okay, we only want to identify the high ones. usually recommend a few items that the user should value highly. We do not want to generate all the values because you cannot recommend 10,000 items to a user. And most likely to generate additional revenue if we can recommend stuff to the user. So key problems. First, gathering the non-ratings for metrics is difficult. How to collect data in the utility metrics, because most people do not rate most items. Extrapolate unknown ratings from the known ones, mainly interested in high known ones. We are not interested in knowing what you don't like, but what you like. Evaluating the extrapolation methods, how to measure the success and the performance is difficult. So this lecture, we are going to focus on here. But let's look at collecting ratings. So two ways. First one, you can start to ask people rate items, right? Explicitly. It doesn't really work well in practice. People can be bothered. You can do implicit learn ratings from user actions. For example, purchasing implies high rating. What about low rating? If the user didn't purchase it, could be it's just the user doesn't really know about that item. If you're running a business like Netflix, you can also use many user behaviors, right? So if a user click on a show, watch the only 10 minutes, and then close the show, come back to next day, watch the next 20 minutes, well, this is probably saying the rating will be 3 from a 1 to 5 scale, right? If the user open a TV show and watch it from the beginning to the end, and then tomorrow watch it again, this is 5, right? The user really likes it. So some behavior, you will be able to extrapolate this ratings. Also, how do we extrapolating this utility metrics? The key problem is the metrics is usually very sparse. Most people have not rated most items. You have some problems like cold starts. New items have no ratings. How do you handle them? New users who do not have any history, do not know about the user, how do you extrapolate these missing values? So one very cool program is called Amazon Vine. I don't know if you guys know about this. You can become an Amazon Vine reviewer and get free stuff. But you have to write really good reviews. I think this is also very common for many merchants on eBay. They will send you free samples and you just write reviews for them. You don't have to be like internet celebrity to do this. But what would be a real problem for Amazon then? Well, think about this. If they want to pay you or send you free stuff to write a review, assuming that you write very good review, so we don't question that. But the question is, remember these metrics. You have movie, you have user, you have many blank spots, and you have limited resources, right? So where should you start? Do you want to pay people to review this or this? We're talking about movies, right? So only columns, or this, or maybe this. As this is still an ongoing research problem. People are looking at different ways to provide reviews, so within a limited amount of resource, so that we can better extrapolate this utility metrics. So 3 approaches to build a recommendation system. We're going to cover all of them. So content-based, collaborative filtering, and hybrid approaches. Content-based approach will use characteristics of an item. So something that you can use, any description of an item. You recommend items that have similar contents to items a user liked in the past, or items that match predefined attributes of the user. And we're going to look at what does this mean. But in general, if you're a user and you have a history of looking at news articles about the Lakers, a good recommendation system, knowing that the contents you like is about Lakers, they might be able to infer things like, all right, you like basketball. So they will recommend other basketball news articles to you, but they might be also inferring that you like sports teams in Los Angeles, right? They would then recommend news articles about Clippers or other teams to you. For predefined attributes, this is actually very common. So many applications will ask you to start to pick a few things that you like, and based on that, they will start to recommend items to you. So for example, if you're using a news app, it will say, are you interested in politics? Are you interested in entertainment? And you select a couple categories. And these are all called the characteristics of an item or the content of an item. So content-based system. The main idea is to recommend items to customer X that are similar to the previous items rated highly by X. So you see here, similar means we have to have a way to characterizing the content of items, and we have to compare them so that we know they are similar. So examples, we just did some examples, but movie recommendations, you recommend movies with the same actor, director, genre, and all that, right? So some people really like romance movies. Other people really like action movies. Websites, blogs, and news recommend websites or news with similar contents, and it really depends on how you define similar. Right? Like in our previous example, could be Lakers basketball, or it could be Lakers Los Angeles sports teams. So what's our plan of action? You have a customer, this customer likes some items, and you have some way to describe the items, right? Look at these item profiles here. What are the things that we can use to describe these two items? Well, color, red, and what? Shape, right? Circle and a triangle. And based on this content, we say, okay, the user likes red, the user likes circles, the user likes triangles, and this is called a user profile. And based on this user profile, we can search in our item database to find what are the things that are red or circle and triangle and recommend it to the user. Okay, so very simple. So general strategy for content-based recommendation systems, we first by constructing a user profile like this red and triangle. But very often, well, sometimes you have explicit features in the database or like tags. But more times, you might not be able to have all these explicit features. You might need to discover features in your items. In this case, it's document. So what does this mean? Imagine you're managing this news archive database, and you want to build a recommendation system to recommend archived news to a user. Each news article will have some metadata that will be your explicit features in the database. Metadata could be publisher, time, and what else? Type, right? Politics, right? Theme, entertainment, sports, and so on. So these are explicit features. These are usually very difficult to get and very limited. And tags are one of them. But also, if you're running a document, we will be able to generate some features to describe this document based on its content. Then we can compare them, and we are going to cover them. It's called TF-IDF. So think about this. Let's not talk about document. Talk about chairs. So if you are selling furniture, what would be a good way that you can characterize your furniture so that you can build a recommendation system? Anybody? Price? Style? Material? What else? That's probably it. But if you're running an online furniture business like Wayfair, you have thousands of furnitures and you only have 3 categories. well, 3 dimensions of your data. And for each dimension, you have to really think about, okay, so let's say style. What would be the style? You can have classic, you can have modern, industrial. You have to think really hard to come up with all these features, and they have to make sense, because if they don't make sense, the user will not be able to use them, right? So creating all these features are actually very difficult for many applications. That's why if we are able to discover them automatically, it will be very useful. So create vectors to represent items once we have these features. For example, we can have Boolean vectors indicate occurrence of high important words. We're going to cover TF-IDF, but if you read your textbook, it's covered in chapter 1, I think. Numerical vectors contain ratings. So now each item is a feature vector. Then we're going to construct user profile and then build a recommendation system, but we're not going to talk about it. Now, we're going to talk about item profiles. So item profiles, for each item, we want to create an item profile. A profile is a set of features, and this is usually a vector. So movies could be screenwriters, title, actor, and director. If your item is text documents, it can be sets of important words in the document. So this is one example from your textbook. Let's say we are going to create this item profile for movies. So features for movies. These are sets of actors and average ratings. Each movie has 5 actors. Let's say we only have 2 movies. We want to create item profile. And for these 2 movies, they each have 5 actors, and 2 actors are in both movies. Average rating is 3 and 4. You want to scale the non-Boolean component, but we are going to talk about this later. Let's just look at this first. So we say we have 2 movies, right? So that means you have 2 item profiles, D0 and D1. And each movie will have 5 actors, and we can use 0 means the movie does not have that actor. Use 1 means the movie has that actor. And 2 actors are in both movies. So how many, what's the length of our feature vectors for actors? 1, 2, 3, 4, 5, 6, 7, 8, right? Because 5 plus 5 is 10, but 2 are in both movies. So minus 2, you have 8 locations. What are the actors in both movies? Here and here. Okay, great. And we have ratings. And look at the alpha here is just a scaling factor, because the scale for all this actor indicators are either 0 or 1, but here you can have 0 to 5, right? So you want to have a scale factor. So from these vectors, we can start to compare them and to figure out the similarity between 2 items. And one way we can do it to compute their similarity is to use the cosine distance. We covered cosine distance last time, but today we're going to talk about, well, next time, we're going to talk about how we actually calculate the angles. It's very easy. It's your high school math. All right, so we're done for today on recommendation systems. I hope you enjoy the lecture today. Any questions? Questions? Are you guys still there? All right, so very important, read your textbook, work on your assignments. Don't ask me what quiz we'll include next time, please. It's the same, always the same. My answer is always the same. Everything we covered after last quiz to today will be the main focus of your quiz, but it could be something before that last quiz because we didn't have the time to test it. Also, we'll cover your textbook. Okay, any more questions? Oh, make sure you work on your assignment 2 and your assignment 3 is coming up, that will be the most time-consuming assignment. But the fun part is you'll be able to use that to build a really nice final project. All right, that's everything I want to say. So someone says assignment 3, the hardest one, is not hard. It just takes time to implement it and to get it right. Because you need to build a recommendation system and you need to build this similarity measurement using min hash and locality sensitive hash. None of these are difficult. It just takes time. You'll be able to do it. Do you guys still go to the TA's office hours? Yes, okay. So make sure you go, or we will just make it 1 hour. If you have any questions about the quizzes, go to your grader's office hour.
Hi, Professor. I have a question regarding homework.
Yes, what's the question?
Yeah, I wonder, do we have to use RDD all the way? I mean, to do those for loops, double for loops?
You have to use Spark.
Yes. So for those algorithms like a priori and or a PCY, actually we are allowed to use regular Python syntax, right?
No, you need to use Spark. Whenever you can parallel process it, you need to use Spark.
Okay. So, for example, if I want to apply a priori algorithm when I am, yeah, hold on one second, let me get back to the, for example, if I want to find a frequent, generate all the pairs, I don't think I can do it on RDD. Because it requires a double for loop.
Yeah, you probably will not be able to parallel process it, right? But for anything that,
I see.
if you can do parallel processing, you want to use Spark.
Oh, I see. I got it. Thank you very much.
Sure. All right. Thank you, everybody. If you don't have any questions, you can leave now, and I'll see you next week. If you want to come to my office hour, you can stay and ask questions.
Thank you.
Thank you.
Hello, Professor.
Yes.
Could you go over the last question on the this week's quiz? Let's talk about the FP growth algorithm.
Sure.
I mean, yeah, during the quiz, I don't have enough time to finish this question. And after that, I complete the whole process, but I'm not sure if my process is right. So I would like
show me how you do it. Show me how you do it, and I can answer your questions. You can share your screen.
You want me to share screen? Okay. Well, I just write down the whole process, and now it has the final result. I'm not sure, because actually, I'd like you to go through from the FP tree build process. I'm not sure if my answer is correct.
Well, if you only want to see the right answer, we are going to, the grader can give you the solution, right? We will post the solution. I think the most
Uh-huh.
important thing is to understand how the algorithm works. So
Right.
if you
Yeah.
want to see me doing it again, you can just watch the video. I'm not saying that I don't want to do it again. I want to help you understand the algorithm. So I think it's better that you try it. And if you have questions, we can work it out here, right?
Actually, I did on the quiz, and do you need my process? Actually, I can share the screen because I saved my
Oh,
the process.
yeah, I think we can definitely exchange our own solution to see if it is right.
Can you see that this is my process? Do you need
Yeah,
to
but
use
my
this?
point is, if we just show you the solution, it doesn't really help you. So if you can work on it here, then we can work together to see what are the things that you don't know, right? Or do you only want to see the solution?
Actually, I want to see the whole process. So maybe it's better that we can work on this question together here.
Sure, yeah,
To
share your
repeat this
screen and you can start to work on the question.
process. But I'm not sure how to make the annotation here.
Oh, you just share this, share a whiteboard and you can then start to draw.
Share the whiteboard.
Yeah, if you click on share screen, you have a choice to share a whiteboard. Or I can share a whiteboard. Then you can draw. Can you?
I see. Give me some time to set out this.
Sure. Yeah, I just think if I just give you the solution, doesn't really help you. If I do it again, it doesn't really help you because you can just watch the video, right? If we do it together from you, that's probably more helpful.
Let's see. So I'm gonna draw on my iPad. So for the FP growth, firstly, we need to count the each of the single item.
Right.
And I just skip this part because I think my count is right.
Okay. Yeah, you can just write down the result.
So the single items are just.
Oh, I don't think I can. I cannot see your drawings.
Really?
Okay, yeah, I can see it now.
So the single items are 1, 2, 3, 4, 5, and the count are just 6, 7, 6, 3, 3, and we need to sort the single item. Firstly is item 2 is 7, item 1 is 6, 3 is 6, and 4 is 3, and 5 is 3.
Okay. Why do we want to sort them?
Yes.
Because when we generate the FP tree, we want to follow the same sequence for each of the buckets.
Right. So, but why do we want to follow this sequence? Why is this important?
We want each basket to share as much as the prefix.
Okay, great. Yeah, so you understand. Great, good. All right, continue, please. Oh,
yes.
We cannot see your drawings. I can only see
why?
single.
Why?
Okay, yeah, now you have
Oh,
it.
it's,
I don't know
oh,
what's going on.
I understand. When I'm seeing the question statement, the sharing is paused. I don't know why.
Oh, okay. Okay, that's okay.
That's
All right,
weird.
so you have this. Nice. All right, next.
Next, we need to generate the FP tree. We start from the null, and the first transaction is 1, 2, 5, and oh, we need to sort each of the transactions item according to our sort sequence. So the first one is 2, 1, 5. So start from null. We have a first node, which is 2,
Yes.
and we count as 1 and 2, 1, 5. We generate 1, and all these are 1, 2, 1, 5. And the second.
Sorry, yeah, I
transaction.
have a question about here. So actually, 3 and 4 is more than 5. So do we need to give a space for the 3 and 4?
What do you mean 3 and 4 is more than 5?
Just like because for the sort consequence is 2, 1, 3, 4, 5. So do we need to still?
You're inserting your first basket, right?
Okay.
Because your first basket contains
Okay.
3, 4? No, right?
Yeah, the first basket only contains 1, 2, 5. The first bucket doesn't have 3 and 4.
Yeah, this is good.
So I'm gonna continue.
Sure.
The second transaction is 2, 4, 5. So 2, we change the count to 2, and we have another node is 4 and 5. And the second transaction is 2 and 3.
Oh, wait, now you have 5, right? So what do you want to do when you have?
We have
This-
5.
Now you have 2 nodes with the same value, 5. So what do you want to do when you have 2 nodes that have the same value? Here, let me show you.
I'm not sure.
You have a 5 here, you have another 5 here.
Yeah, but they're from different prefix.
Right. But even when they are from different prefix, you still want to generate a link, right? These are the
Oh,
dash.
right. Yeah, there's a link, right? But the
So-
tree structure is still this one, right?
Yeah, it's a prefix tree.
Right.
So why
There's link
why
here.
do we want this dash lines?
I think it's it's for later process when we need to generate the conditional pattern.
Yes,
We
great.
need to follow this link to have all of the same
Yes,
same value, same item.
yes, great. You can continue, please.
So the third transaction is 2 and 3. So we share the 2. Now it is 8, and we need to have a new node, which is 3. Now the 3 is 1 count. And the fourth transaction is 2, 1, 4. We share the same 2, and we share the same 1. And 4. For 4, we need to generate another node, which is 4. And right there should be another link to this 4 node.
Okay.
And
2, 1, 4.
2, 1, 4.
Yes.
And the fifth transaction is 1 and 3. So start from now, it doesn't share the same prefix, so we need to generate another node. Should be 1, and this one have the sub node is 3, and we also need to have a link between the 3
Yes.
and the 6 transaction 2, 3, 4. The 2 we shared 2 to 5. 3. Is there 3? Yes. 2, 3, 4. And the seventh transaction is 1, 3. So it's just 2 and 2. Here should be a link. And the 8th transaction is 2, 1, 3, 5. 2, 1. I'm going to have another node. 3 and 5. So for the link here, I'm not sure. Should we follow the sequence? We need to generate a link like this.
Oh, the dash lines? Yeah, always the last one, because in your memory, you will keep the last one.
We'll only keep the last one. Okay. So the 4 should generate like.
Yeah,
this.
so think about this. You don't have to keep the previous one because you can use the links to find the previous one. Wait, this is wrong.
2, 1,
So
4.
you don't have this. This is a search.
Oh, right. There's no dash line here.
But for your
Okay.
3-1 here, you need the dash line. Right, this here.
3, 1 from the.
Right.
Oh, right.
Always look at the last one.
Right. Well, this tree is really. It's a mess. Which
That's
one?
okay.
2, 1, 3, 4. And the last transaction is 2, 1, 3. We should be 7. 1, 4, 3, 2. So this is a FP tree, I think.
Yeah, looks good.
Okay. So after this tree, we need to generate the conditional pattern base. So for the conditional pattern base,
Where do you start?
we start from our sorted single item, right?
Yeah, you can do that.
It seems that the sequence is the reverse sorted of.
Right. So why do you want it to be reversed?
I'm not sure this part why.
Oh, because you always want to start from the leaf, right? You're going to start working on this, and you get the subtree, and you work your way up. So you reverse the order. You start from the single item with the smallest count or smallest subrow.
Oh, so the reverse sequence makes sure that we start from the bottom to top.
Right.
Okay. So the conditional pattern base, we need a table item, and this item should be the reverse order. It should be 5, 4, 3, 1, 2, and
Then you start to look at the conditional pattern base and frequent pattern base.
so we need to refer the FB tree. We start from 5 and
Yeah,
we
I think you
count.
can just do the item 5 and everything else should be similar. So let's look at item 5. What will be the conditional pattern base?
Let's see, I'm not sure. 2, 1, 5. 2, 1 is count as 1. So conditional base, how to represent, should be a tuple.
Yeah, should be something like this, right? 2, 1, and once.
Oh yeah, so just write down 2, 1 with count 1 and
It doesn't
5.
really matter how you write it, as long as you get it right.
Okay, so then we have 2, 1, 3.
Okay, so 2 and 3, what's the count?
And
okay.
we also have 2, 4.
Okay.
2, 4 as
Right.
count 1.
Great. So what does this tell you?
That's 8.
This tells you 2, 1, and 5 were in the same basket once. 2, 1, 3, and 5 were in the same basket once. 2, 4, and 5 were in the same basket once.
Right.
Then based on this, you can start to generate your conditional frequent pattern base. So what would be your frequent pattern base?
The single item is 2 as count for
right, 2
as 3.
Okay, yes. That means what? 2 and 5 has appeared
1,
in
5 is
3 baskets, right?
Right.
Okay, so what else? What else do you have?
We have 2, 1 as count 2.
So 2, 1, 2, 1. Okay, great. What's next? Do you have 2, 4?
That only count 1.
Right.
2, 4.
And your support is 2, right?
Right. So it only generates 2 conditional frequent.
So, no, you have another one.
Which one?
You have 1.
Oh, right. 1 as count 2.
Okay.
2,
Yeah.
1,
Okay.
1.
So now you have every frequent pattern base. Now you can just start to generate your frequent pattern. What will be your frequent pattern?
2, 5.
Okay.
2, 1, 5, and 1, 5. So this should be the frequent.
Yes, correct.
Frequent item for item 5. It ends with item 5.
Yeah, and usually you will also write their support, because later when you calculate your association rules, the supports might be useful.
Right.
So you're done. You're good. I don't think you have any questions. What's your question?
Okay. Yeah, I think it's obvious for the other items.
Yeah, it's the same for every other.
Yeah. Thank you.
Good job. Very good. Very good. All right, any more questions, guys?
I think I have questions about LSH. Let me see. Yes, could you mention one more about this graph? So how like the threshold and probability like?
What would be the specific question?
Oh, yeah, actually I forgot because let me see. Yeah, so like the ideal SP curve is just like this, and why it will be a curve like this.
Oh, because this curve is determined by your P function, right?
1 minus yeah. Okay.
So based on this function, you will never have this.
Oh. So just like when the S and P so actually my question is how like if the S increase and what will the curve become?
If you increase S,
Yes.
S is here,
Increase S
right?
and P. Yeah, this is S. Yeah.
So P and S is your exit. So you're not going to, I'm not sure what do you mean by increase them though. Because this function is determined by your R and B,
Okay.
right? So if you have a larger S, you just base on this function to find a P.
Okay. Got it. Thank you very much.
Sure.
Okay. So for Simon 3, there will be 2 parts. The first one is about min hash, and the second one is building recommendation system.
Yeah.
Okay.
But in general, for your final project, you should be able to use min hash
Okay.
and locality sensitive hashing to improve your recommendation system.
Okay. Okay. Thank you, Professor.
Sure. Thank you.
Thank you.